open and closed tubes. Wind instruments create sound through standing waves in a column of air, and we talked about that earlier with the saxophone picture. Although some instruments are curved, it is easiest to think of just a straight column of air. Instruments that are open to the air at both ends are modeled as an open tube. Instruments that are only open at one end are modeled as closed tubes. Flutes are examples of open tubes. Clarinets, oboes, saxophones, and trumpets are closed tubes. Organ pipes can be designed as either open or closed. The fundamental wavelength of a standing wave in an open tube is twice the tube length. The fundamental wavelength of a standing tube in a closed tube is 4 times the tube length. So 2 times, 4 times for the wavelength, the fundamental wavelength. An open tube has the same harmonic structure as a string. So here's the string, which was in the last unit, and you have a node where there's no disturbance, and then an antinode, which is the maximum. Then, if you look at the sound wave over here and you're measuring the air pressure variation, it's highest in the middle and 0 at the end. And your first harmonic, which is called the fundamental frequency or fundamental wavelength, here's the wavelength, twice the length, and then the frequency is V over lambda. Then you have other harmonics, a first overtone, a second overtone, or just called the second harmonic, because here's your first, here's your second, and there you can see what happens to the wavelength. It gets cut in half, and here it's 2/3 of the length. A lot going on this slide, so you may want to pause it and just look at it for a bit. If instead of air pressure variation, which we showed on the previous slide, you look at air displacement, how much the air is moving, the nodes and the antinodes are switched. That's because if you're open at both ends, your pressure at the end is going to be the same pressure as you have outside the instrument. However, the air, it gets displaced more. It's got a maximum at the endpoints, and then right in the middle, it's not displaced at all. It goes something like that. In general, we will solve problems with the antinodes at open ends of the tube, because this is how the air inside the tube is vibrating. That's how the molecules are physically moving. Since there is an antinode at each end, multiples of half wavelengths will fit inside the tube to resonate. And why is that? Well, let's see. If we said we had a node at the beginning, like this, and then you traveled like this, well, in this case, since physically you have antinodes at each end, you can't have something like this, right? Those are nodes. But you could have this piece over here as it comes down to here. Then you would have an antinode at either end of your pipe. So a tube open at both ends like a flute has pressure nodes and therefore displacement antinodes that we showed on the previous slide at both ends. So here's our displacement antinodes. Here's one. The wave will oscillate between these two places. It goes like that, and then it goes like this. So in that case, your wavelength is equal to twice the length, because you only fit half a wave inside your tube. Then you find the frequency by velocity over wavelength, and that's going to be your fundamental frequency right here, your first harmonic. Then you take your next wave that's going through, and it looks like this. In that case, your wavelength is equal to L. And you do the same thing for frequency. Your fundamental frequency is twice the original one. And then you have 3/2 waves fit in. This time your wavelength is 2/3 L, and your frequency now is 3 times the fundamental frequency. The general equation for the wavelength of an open tube then is this: lambda sub n equals 2L over n. Now what is n? Well, that's going to be the number of nodes. So n is equal to 1 for the first harmonic, 2 for the second harmonic, 3 for the third harmonic, etc. And it's also the number of nodes. So let's find the frequency. That's V over lambda. Now since we have the subscript for frequency, we also have the subscript for the wavelength. So that's going to be V over 2L over n. That's lambda n right there. Then we just move the n up top, and we have n times V over 2L. And the previous slide showed that this was the first frequency, the fundamental frequency, the first harmonic. So we substitute that in, and then we get F sub n is equal to NF1. And let me just erase all this so you can more clearly see the equations. And there you go. Now let's look at a closed tube. The end of the tube here is solid, so it is much denser than air. When the wave reflects off the end of that tube, it inverts. Therefore, there must be a displacement node at the closed end of the tube. And there you have it. The open end of the tube, over here, will still have the air vibrating back and forth across the opening, so there must be an antinode at the open end. And there's your antinode. Well, those are antinodes. And just to make this picture clear again, the wave first looks like this, then a little bit later it oscillates down like this, then it goes back up to the top again, etc. In this case, only odd multiples of quarter wavelengths can vibrate in closed tubes. A tube closed at one end, such as clarinets and some organ pipes, has a displacement node and pressure antinode at the closed end, right here. So we have a displacement node. This time, the first wave you can fit in there that goes from a node to an antinode is only a quarter of the wavelength. So let's show a quick picture there. Here's a wave. And the first time you have a node is here. And then you have your antinode here. So what is that? That's a quarter of the wave. This thing here is what's being drawn there. So lambda is equal to 4L. So your fundamental frequency will be V over lambda, V over 4L. Here's your fundamental frequency this time. Now, what's the next wave you can fit in there? You can get 3/4 of a wave. So that means you go up like this, come down here, and wind up over there. That's 3/4 of a wave. So your wavelength this time is going to be 4/3 of the length. We do frequency again is V over lambda. We get 3V over 4L, and it's 3F. Then one more time, you get this picture with 5/4 of a wave. Lambda is 4/5 of L. Plug it in, and now you get 5 times that fundamental frequency. So we've gone from 1F, 3F, 5F. The equations for closed tubes are similar to open tubes, except the tube becomes a 4 to represent the quarter wavelengths, right? We don't have half wavelengths this time that fit. We have quarter wavelengths. That's a quarter wavelength here. Since only odd multiples of quarter wavelengths will resonate, n is restricted to odd numbers. So we have our frequency n is n times the fundamental frequency there, F1. Remember we found that on the previous slide. But we also found out that n can only be odd numbers. So there's our closed tube equation. And again, I'll go ahead and erase my markings there. The harmonics are very, very important, because why does a trumpet sound different from a flute or a piano when they play the same notes? The answer lies in the harmonics. Those are the multiples of the fundamental frequency. Which ones are present and how strong they are make a big difference. The plots below show frequency spectra for a clarinet, a piano, and a violin, illustrating the differences in overtone strength. So looking at this, and it's way more complex than this, but this is pretty close. Let's say here's your fundamental frequency. You've got your frequency here and relative amplitude, how strong that frequency is, how much you hear it. So that matches with the violin here. And look, for the piano, you've got a whole bunch of different frequencies there right alongside the fundamental frequency. The clarinet looks very similar to the violin here, but has many more higher frequencies that have a certain amplitude that you can hear. And the piano is way spread out, but it has a whole bunch of little amplitudes with a bunch of different frequencies. So that's why they sound, one of the reasons they sound very different. So please click here for a video on sound and timbre. Yep, that's how it's pronounced, timbre. Musical instruments have characteristic sounds due to the relative amounts of each harmonic present, which depends on their physical construction. The guitar string, and you see 6 strings there, contain many standing waves of a variety of frequency, or harmonics. What we hear is the mixture of these frequencies, and this is called the timbre. And we wrote this down so you don't forget that. You can see hopefully you can see the waves of the string vibrating there with this fast camera. A pipe open on both ends, which makes it an open tube, has a length of 2.1 meters. What are the first three wavelengths that will resonate in the pipe? Well, we're given the length of the pipe, and we're also told that it's an open tube. So we use the open tube equation, which is 2L over N. So lambda 1 will be 2L over 1, lambda 2, 2L over 2, and lambda 3, 2L over 3. Open tubes have N is equal to 1, 2, 3, 4, etc. We then substitute in the givens here, and we get the first wavelength is 4.2 meters, the second is 2.1, and the third is 1.4 meters. A pipe open on one end has a length of 0.8 meters. What are the first three frequencies that will resonate in the pipe? Now, when they say open on one end, that means we call it a closed tube. And you might say, why closed? It's open. Well, if you had both ends closed, you couldn't have the sound escape. I mean, let's assume this is a very heavy pipe, so not much sound is going to get out. We wouldn't have a problem that we could solve. So a closed tube is open at one end. We have the given length, and this time we're going to write the velocity down because we need to find the frequency. We're going to use the closed tube equation, which is this, and be sure to use the 4 here. We had a 2 there with the open tube, and also this time you can only use N values that are odd, 1, 3, and 5. So F1 is 1V over 4L, F3 is 3V over 4L, and F5 is 5V over 4L. We substitute in our givens. Here's the speed, and then here's our 1, 3, and 5. Calculate it out, and we get these three frequencies here for the first frequency. Then the second frequency, even though it says F sub 3, it's your next harmonic, and then F sub 5 is your third harmonic. A pipe open on both ends has a fundamental frequency of 125 Hertz. What are the next three harmonics that will resonate in the pipe? For an open tube, the fundamental frequency is F1, and we're told that it's 125 Hertz. So here's our fundamental frequency, N times F1, so that's the 125 Hertz when N is equal to 1. But we asked for the next three. So we need the second, third, and fourth harmonics, which is twice the fundamental frequency, 3 times, and then 4 times. Substitute in our givens over here, and we get the next three harmonics are 250 Hertz, 375 Hertz, and 500 Hertz.